Now that we've looked at generic discrete probability distributions above, now let's look at one of the most important probability distributions around, a discrete probability distribution. It's called the binomial probability distribution. We've seen it in the second module, even though I didn't give it by name. So for example, in a binomial we have two occurrences, events, two events. It doesn't have to be basic. You can always think of it as a coin toss. But sometimes events which are can be made into two events, but those two events are actually compound events. For instance, people under 40 versus over 40. Okay, and of course the 40 is an arbitrary break, unless of course you're looking at discrimination in employment. But in any case, we could make that split anywhere. But still, we still have two events, right? Over 40 and under 40. The events are independent. Again, easiest thing for you to do is to think of a coin toss. Alright, so that means we're essentially sampling with replacement. Alright, and as I said, we've seen that event before, so let's just do a simple distribution. Alright, we're going to toss the coin 3 times, and X will be the number of heads. Alright, so we know that the event space for X will be 0, 1, 2, or 3 heads. Alright, so 0, 1, 2, 3, and then we could work out the probabilities for each of those. At this point, we're going to work out the probabilities from scratch, and after a while you'll want to do it another way for more complicated problems, and you don't want to do it from scratch every time. Alright, remember X is the number of heads, so probability that X is 0 is essentially the probability of being a tail, a tail, and a tail. There's only one way of doing that. So half times a half times a half, and that's 1/8. Okay, 0.125. Since it's symmetrical, then the probability of X is 3 is 3 heads, right? Same thing. Probability of X is equal to 1, that's the probability of 1 head. Right, then you have to do your business probability, the number of ways times the probability of 1 way. How many ways are there of getting 1 head out of 3? Right, head, tail, tail. Tail, head, tail, 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 head. Alright, 3 ways. Times the probability of 1 way. Alright, head, tail, tail. Well, that's still a half times a half times a half. It's 3/8. Or 0.375, and as we'll see, this distribution is symmetrical, so this is also 375, and when you do the addition of those, you'll find that it adds up to 1, as it should. Alright, so that's a binomial probability distribution where we usually like to know the n, the number of trials, in this case 3 tosses, and p, the probability of one success on one trial, in this case will be the probability of one head on one toss, and that's a half. If we have another situation in the world but n is 3 and p is a half, we still have that same probability distribution as long as the events are independent of each other. If the probabilities change from 1/2 to like 0.4, 40%, of course the probability distribution will change. And of course also if the n changes, the probability distribution will change. It's more obvious. Right, we can do everything that we did here, that we did in the generic probability distribution, so we can do this to this distribution. Right, we can find the mean, variance, talk about different probabilities. Okay. In general, though, we don't want to do it from scratch, so we use, if we don't have probability tables to help us, the binomial formula. And that formula goes like this. So we talk about the probability of x occurrences, n the number of trials, the number of successive events, p the probability of so-called success, the thing that you're looking for on one trial, and that's equal to, we'll write like this, ncx p to the x power times 1 minus p to the n minus x power, where ncx, alright, so this formula is nothing more actually than the number of ways, that's the ncx, times this part here is the probability of one way. But ncx then is the number of ways, and that's written as, and again I'll have to explain that, n with an exclamation mark, which is read as n factorial divided by x factorial n minus x factorial. As an example, 4 factorial is 4 by 3 by 2 by 1. You stop at 1 always. Okay, so 6 factorial be 6 by 5 by 4 by 3 by 2 by 1. We can work that out, but it's a big problem. Alright, so again, n factorial divided by x factorial n minus x factorial. So if we were talking about the probability that, as we did above, x is equal to 1, where n is 3 and p is equal to a half, we would write that as, alright, look at the formula if you have to, ncx, so 3c1, which will tell us the number of ways, times p, 1/2, to the x power 1. Right, so it's the probability of getting one head, and then we have 1 minus p, probability of getting a tail, and we get 2 tails, so square that. Okay, 3c1 is 3 factorial divided by 2 factorial 1 factorial. 3 by 2 by 1 divided by 2 by 1 times 1. Alright, so the 2 by 1 is the 2 factorial, the last 1 is the 1 factorial. 2 by 1's, 2 by 1's cancel, and you're left with 3. Okay, that's the same answer that we had before. Alright, that's 3/8, 375. So, we can do some really big calculations, and they're sort of easy. Alright, even your calculator might die on some of them. Let's say that we had to calculate 100C98. Okay, you're looking for 98 good parts out of 100. Of course, then 2 defects. Anyway, that would be 100 factorial divided by 98 factorial, 2 factorial, and some of you are thinking to yourself, 100 factorial is real long and I'm not going to write all that out. You're right, I'm not going to do that. But think about it, 100 factorial is 100 by 99 times all the rest, and all the rest can be written as 98 factorial. And the 98 factorial is on the bottom, and so that cancels with that. Wow, well that disappeared real fast, right? And then we still have 2 factorial times 2 times 1, so this just boils down to 100 times 99 divided by 2 by 1. Okay, and that's easy. Do that. Okay, I'm not going to work it out right now, but that's an easy thing to do. Alright, so don't shy away from these things. They're sort of easy to do. Alright, let's do a few. I'm going to do one more, and then hopefully you will try these problems before you see me do them. Alright, next one, let's look at the probability that x is equal to 5, where n is 10 and p is 0.3, and use the binomial formula, of course. Okay, so this boils down to ncx 10c5 p 0.3 to the x power, the 5th power, times 1 minus p, 0.7 to the n minus x, 10 minus 5 is also 5. Alright, 10c5 will be 10 by 9 by 8 by 6, sorry, by 7 by 6 by 5 factorial divided by 5 factorial times 5 factorial, 5 by 4 by 3 by 2 by 1. This 5 factorial cancels with that 5 factorial. 5 and 2 makes 10, cancels with the 10. Alright, and then we can go from there. Alright, so that gives us 3024 on the top divided by 12, and that probably goes in nicely. And we're still left with 0.3 to the 5th times 0.7 to the 5th. And I'll pull out my calculator and work that out. And I get that that's equal to 0.1029 to 4 significant places. It turns out later we will be using some binomial probability tables to calculate some of these probabilities, not all of them. This one you could actually use your tables to work that out, and when you're rereading this after you've seen the whole thing, you might actually try that with the tables later.